Okay, so I'm going to talk about mainly about some theoretical ideas, actually, and some work, especially that's been done by Katerina Poistova, Mi Zhang, and Ilya Elfimov. And I'm going to talk about the combination of cluster calculations and hybrid density functional. I am not an expert in either of those, so you have to talk to the actual experts who are Katarina and me and Ilya. And I'll talk a bit about Zhang-Rai singlets versus three-spin polarons. I think you've all heard a lot about the Zhang-Rai singlets, but maybe not so much about the three-spin polarons. And about super exchange interaction, which is, of course, antiferromagnetic. But three-spin polaron interactions are ferromagnetic, and they can actually produce these stripy phases and things like that, up, up, down, down, and things of that kind. And a bit about the coupling of spin and charge. So I think the spin and charge are very strongly coupled in these systems, and the possibility of ordered three-spin polaron states and cuprates and nickelates. And this is very much related to what Subir Sachdev has been talking about a lot in the last while. And these are some of the papers that have been involved in that, including also the paper that Subir also talks about a lot at the bottom. Um, so very basic, first of all, hydrogen molecule, you know that we have two ways of doing it. One is to have the molecular orbital scheme in which you put two electrons in a bonding state and they have a spin of 0. There is no triplet associated with that particular state directly. If we want the triplet, we have to first make an excitation to the anti-bonding state, and that already tells you very clearly that you have strong coupling between the wave function and the spatial wave function and the spin actually of the system. Okay, and on the right-hand side, you have the Heitler-London model in which you have Coulomb interaction U and the exchange interaction. You have singlets and triplets. Exchange interaction is T squared over U. Now, the cluster versus DFT can actually identify the identify which state should be more MO-like and which should be more Heitler-London-like. And I just want to remind you about the Hamiltonian, Heisenberg Hamiltonian, where S dot S is S Z times S Z plus 1/2 S plus S minus plus S minus S plus. And it's that last part that is not really possible to do properly in density functional type or molecular orbital type approaches. The energy of the triplet is 1/4 J, and the energy of the singlet is -3/4 J, and that shows that the singlet has very strong quantum fluctuations in it. It's also very important to realize that the ordinary mean field energy of an antiferromagnetically ordered spin 1/2 lattice, the energy is equal to minus Z, which is the coordination number, the number of nearest neighbors that are coupled, times N, the number of atoms, times J divided by 8. The 8 comes from the N over 2 times 4, which is the 1/2 times 1/2. And the singlet liquid energy is -3 NJ. So you see immediately that if we reduce our number of nearest neighbors from 4 in a two-dimensional like system, that we can very quickly get into a singlet liquid phase being the lowest energy state. And that's what Subir also emphasizes very much, and so do many other people. Now, we all know what the Zhang-Rai singlet type picture looks like, and many people think that if I have that, then I can relate this system to a single band Hubbard model, which actually I disagree with very, very much. But basically, this is the idea that the 4 oxygens around an x squared minus y squared orbital with the right phases, they will hybridize twice as strongly, actually, than the single bond hopping integral. This is the effective hopping integral for the between oxygen and copper for the Zhang-Rai singlet. And the equations, are you guys seeing this stuff down here?
Yeah, I think
This,
so.
yeah. Why is that? Don't know how to get rid of it. Anyway, the exchange interaction is these hopping integrals therefore get so large that the exchange interaction really can no longer be calculated by perturbation theory, and you really have to go on to doing things in a proper calculation. And this is the CuO4 calculation that Estes did many years ago. And in that calculation, you see the singlet A1 and the triplet A1, which is the x squared minus y squared oxygen and d orbitals forming a singlet or a triplet. And you see that energy scale there, it's 4 electron volts. It's the difference between them. But that is actually mostly a molecular orbital splitting and not so much an exchange interaction. So one has to be very careful about this. Now, these Zangrai singlets, they actually exist. Look at the right-hand side plot here. They actually exist only close to pi over 2, pi over 2. In the center of this diagram is pi over 2, pi over 2 in the Brillouin zone. And these other kinds of combinations of oxygen orbitals that you have, they are either in the corners of the Brillouin zone and or this gray region, which is spread out over a very large range of the Brillouin zone. Now that's very important because the phases of the wave functions are such, and you can see that in the diagram below here, that this is a Zhang-Rai singlet-like phase. It has x squared minus y squared like orbitals, but you see that these oxygen orbitals have to be flipped around. And this is the nearest neighbor along a 1-1 direction along the diagonal. And you see that that works very nicely. Also, and this is at pi over 2, pi over 2. This is very strongly dependent on the wave vector that you're actually looking at. If you look on the other hand on this side, you see that the phases are exactly opposite. So this is a plus and that is a minus phase. And this is actually the three-spin polaron-like object in which you have two antiferromagnetically coupled antiphase singlets. And they form actually a ferromagnetic coupling between these two copper spins, which are in the middle. Okay, so this is the calculation of a very large cluster by Bio-Lau, and he shows that in this cluster, you can, this very large cluster, which is 32 copper atoms and 64 oxygens with one hole, okay? And you can see beautifully the hole dispersion looks very much like that you also get in the TT prime double prime J model, which is the triangles, these blue triangles that you have here. But you see something very strange, that the lowest energy states are all spin 1/2 states, the energy removal state. If you remove one electron from a spin 0 state, an antiferromagnet, it should be spin 1/2, and you see that. But at 1-1 here at this point and at gamma, you see that the spin 3/2 state is the lowest energy. And this is very interesting because these things can be described very well with a three-spin polaron model. You also see in the bottom here that the same kind of thing happens as in the TJ model, except that it's much more extreme. Your spectral weights are very strongly dependent now on momentum. And that is also something that you see in angular resolved photoemission. Of course, in photoemission, you wouldn't see these spin 3/2 states. And indeed, you don't see anything at pi over for a single hole at 0, or at gamma or at pi. Okay, so the three-spin polaron, what Bio also calculated was what is the spin correlation between the neighboring copper atoms with an oxygen in between. Okay, and you find out that it's ferromagnetic. Yeah, and I already said that it would be ferromagnetic. Far away from that hole, the hole is here, and this is a diagram with K in the pi over 2, pi over 2. K is equal to pi over 2, pi over 2. And then you get this kind of a plot. So far away from that hole, of course, the correlations are the quantum fluctuating antiferromagnetic fluctuation, which is 0.33. Okay. On the right-hand side, you see what happens at pi pi, where you have this triplet, where you have this 3/2 spin state. And you see that there's even stronger. It doesn't yet look like a 3/2 state, like a ferromagnetic state, or a spin, spin 3/2 state. But yeah, it's still got a much more positive, like correlation. Um, the three-spin polaron, let me just has the three-spin polaron has namely can have a spin of a spin of 1/2 or a spin of 3/2. There are two spin 1/2 like states, one of which in which the copper spins form a singlet, and the oxygen spin then is free to move. And the other one, and that's very important because if you have a spin that singlet liquid, the oxygen can freely move. If, on the other hand, you don't have a singlet liquid, but an AL antiferromagnet, then you may want to, then you have these states as the lowest energy state, the spin 1/2 state, which has this combination of up, down, plus down, up for the copper. That's an MS is equal to 0 state for spin 1, with the oxygen spin up, minus 2/3 times the up, the MS is 1 state of copper, and an oxygen spin down. And the energy of that is -1, and the energy of the singlet state over here, the other spin 1/2 state, is 0 in units of JPD, JDD, actually. Okay, and this just shows you actually also what the spectral weight would be. You find out that the overlap integral of an EL antiferromagnet with a sudden removal of an electron with a certain spin on the oxygen, with the actual eigenstate here, that squared is equal to 1/6, and that's actually pretty close to what you see in his calculations. Now, I'm going to run out of time, so I'm going to go through because I really want to get to. I really want to get to the real important part. So let me. You all know about the nickelates, and there's two kinds of in the cluster calculations. We find that there's two kinds of possible ways of putting the fifth electron, or if you make all the nickels 2+, okay, then in such a cluster like this with two nickels vertical, then you would have 4 on the nickel, and you would have 1 extra hole per 2 nickels, and it could be either staggered like the left-hand side is between the two planes, or they could be like this. And we find actually from the calculations, both in the cluster and in the density functional, that these are very much localized in the XY plane, and there's very little hole density in the ground state. And that is shown over here, actually. If you would have the hole in the apex oxygen between the layers, then the spin state would be 3/2. Okay. And if it's in the middle, then it would be a spin of 1/2. And I'm not going to go through this. We actually also looked at what the weights are, and you find out that the weight of the ground state is almost totally in this D8 ligand hole state. There is quite a bit of mixing with D7, D8, so that's the covalency part, and that brings you more into the molecular orbital-like regime. And I'm going to skip through this, actually. Our density functional calculations, on the other hand, and these are the hybrid functional calculations by Katerina, they actually show that these phases where you have unequal spins, these spin density and charge density wave phases. There's two kinds of spin confusions about spin density waves. There's one that is a real spin density wave, which is the magnitude of the spin is varying, and the other one is what the ordering of those spins is. So that's a more order disorder phase question rather than a actual spin density wave. And these magnitudes of the spins are very strongly coupled to the charge density also. So they have the same wave number actually as the charge density does. Okay. Uh, we actually find that this particular state here, which is ferromagnetic, actually looks kind of strange, but it could also be anti-ferromagnetic, but then longer range, because this is a 2x2 cluster uh, or unit cell. That this type of ordering actually is one of the most important. You always have an anti-ferromagnetic ordering between the planes and a ferromagnetic ordering and in the plane, it depends. If you have a three-spin polaron, it would be ferro. If you nearest neighbor would be ferro, and those could be aligned anti-ferromagnetically. Okay, those new spin one-half three-spin polaron states can be aligned anti-ferromagnetically. This is just the what you find in density functional theory if you force it to be ferromagnetic. Okay, in that case, you have the 3z squared minus r squared orbital, empty right above the Fermi energy here, forming a molecular orbital with the apex oxygen, which forms an extremely narrow band in this particular phase. Okay. If you now go to this five-hole case, then you find that the hole density is primarily, this light blue is primarily in almost totally in the x squared minus y squared plane. And if you look at the one where this plane over here, what happened here? I went to, then you see that you again have this molecular orbital formation between x squared minus y squared and the combination of x squared minus y squared of oxygen orbitals. So this now is more in the molecular orbital limit, and I already warned you that from the cluster you also find that this probably happens. I want to go on to, by the way, the density functional theory also tells you that if you relax the lattice, that you actually get quite a large distortion. So the one that has the Zhang-Ray singlet-like state, shall we say, nickel oxygen distance changes by 0.1 angstrom, actually. Whereas the apex oxygen doesn't really do well. It actually also changes by 0.1 angstrom. That's the outer object. The inner one doesn't change at all, actually. So this is an important fact and is suggestive of a strong electron-phonon coupling. Now, I want to, before I go here, I want to show you what the calculation looked like. This was the cluster calculation. And this is done in an octapartite lattice. You see this gray thing here? So you can put 8 coppers in here and the corresponding oxygens between the coppers in the right directions, okay? And then you can stack this in this way, okay? And that forms, if we had that kind of ordering, this would be 1/8 if we had one hole at the center of each of these, okay? Then we would have 1/8 doping. This is what Subir talked about. This is this 1/8 doping, which if you had that, and if you would have a band structure of objects that were centered here in this way, then you would have a Fermi surface which would be centered about pi, and not about pi over 2 that we all expected it to be if it was a Zhang-Rice singlet. But if it is a 3-spin polaron, you actually, as bio has, then you actually would get, indeed, your Fermi surface would be centered about pi, and and you could even get these ordered phases occurring at 1/8. You can also get ordered phases occurring at 1/2. This is this kind of an ordered phase of a 3-spin polaron, like this. Okay, and then going on, this would be a 1/2 type of ordering, and you can also get an ordering like this, which would be which is a quarter actually, and it would form this this ferromagnetic coupling in these stripes. Oh shoot. The ferromagnetic coupling in these stripes, and it would create an anti-ferromagnetic phase boundary, between the anti-ferromagnetic coupling spins on one side and the other, as people think is happening in the cuprates for the charge density waves in the cuprates. Okay, so these would have the 1/4 type of density wave. Okay, so let me just put up my conclusions. I think the most important conclusion that I have is, as suggested by Kaliulin, uh, the pairing glue could happen via the exchange of the singlet triplet excitations between the dz squared orbitals, which are left with a spin 1/2 and have super exchange with the central oxygen between the planes, and the x squared minus y squared are forming this electron gas, same as in the cuprates. But now this singlet triplets exchange excitations, virtual excitations, can be exchanged by two particles, one in the upper plane and one in the lower plane. And that can give you a very nice coupling for superconducting pairing. And this can also happen via the singlets that are in your combination of 3-spin polarons and corresponding singlet background. Those singlet triplet splittings could also be the pairing type mechanism in the cuprates. Thank you.
Thank you, George. Questions for George? Chimiao?
Yeah, I have a question, George. So there's some indication that for these 3 to 7 bilayers, the superconductivity sensitively depends on whether the Z square states, the gamma band, crosses the Fermi energy or sinks below the Fermi energy. And I was wondering whether, from your perspective, does that factor in some way?
I think that's indeed very, very important, and that's why I stressed that we find both in the cluster calculations and in the density functional calculations that the states where you have the apex oxygen occupied are much higher energy states than if you have the holes in the x squared minus y squared or the xy plane. So our also in the cluster calculations, this green part that I had in the phase diagram here, this one, the green part in the upper left corner, that is where you would have the holes. What would happen if you had holes in the oxygen between the planes? And then the dz squareds, of course, are forming a 3-spin polaron with that oxygen. What we don't have in these calculations, and that's very important, I've now talked about also in plane 3-spin polarons. And we haven't done because those require an even bigger cluster, and that has not yet been possible actually to do. So, but I'm pretty sure that those would be also probably 3-spin polaron-like objects, just like we find in those very large cluster calculations of the cuprates.
Okay, thank you.
All right. Thank you so much, George. And as we